Welcome. Let's start to talk about the electric field. The concept of field introduced by Michael Faraday in the 19th century is one of the most powerful ideas in physics. This concept has been extended from electricity and magnetism to gravity and the nuclear forces. The electric field is a perturbation that electric charges create in space. Other electric charges feel this perturbation and are affected by it. The effect of the perturbation of the electrical charges is the electrical force. We can think that instead of a direct force between two electric charges, the charge 1 perturbs space and this perturbation acts on charge 2, and charge 2 feels an electric force consequently. This electric field, this perturbation, is created in every point in space. Because it is charge 1, the one that creates this perturbation, the electric field only depends on charge 1 and the distance to charge 2. Each point in space will have a different perturbation, a different electric field. The electric field is a vector field. This means that the perturbation can be thought as a vector at each point in space. The electric field is written as E is equal to 1 over 4 pi epsilon naught times Q over R squared. This is the electric field at a point at distance r from the source charge. If a second charge were placed at that point, it would feel that electric field, and it would experience an electric force due to this electric field. The electric force that a probe charge experiences, let's call it charge 2, is proportional to the electric field at that point and is given by the electric field times charge 2. This is Coulomb's law written in terms of the electric field. There is no need for a probe charge for there to be an electric field. Nevertheless, we need a probe charge to test that there is an electric field at that point. Of course, because of the superposition principle, if there are several charges at play, the net electric field at a point is the sum of the electric fields of all the charges involved. This net electric field will be the vector sum of all the electric fields. Another way of thinking about this is by writing down the total force of a distribution of charges acting on a probe charge. Then we can factor out the probe charge and we get that the force depends on the probe charge times something that does not depend on the probe charge. This something exists no matter the presence of the probe charge, and it is the electric field of the distribution of charges that we have. Let's now calculate the electric field that these two charges create at a point P. I will calculate the electric field created by each charge at that point and will then add them up. I consider this to be a two-dimensional problem, so I have to calculate the x component and the y component. For that, I have to project, so I need to know the angles the field vector makes. I will first calculate the x component of the positive charge. Then I will calculate the y component of the positive charge. The electric field of that positive charge at that point points up and to the right. Then I calculate the electric field of the negative charge. For that, I also project x and y axes. The electric field of the negative charge points down and to the right. Because the charges are at the same distance to the point P, and because they have the same magnitude in this particular example, the vertical components cancel out, but the horizontal components add up. The electric field at that point points to the right. May science be with you.